single pollutant system. So for this study, the objective of this study is to evaluate the thermodynamics of the multi-components modeling using extended Lagrangian and extended Freundlich isotherm, and also to develop a novel artificial neural network model to represent the equilibrium adsorption behavior for the binary system, because the extended Lagrangian and extended Freundlich they assume that the system is ideal system that is based on an adsorption, and most environmental systems sometimes do not follow this adsorption. So a developed neural network model will put all this into consideration, and finally to evaluate the interactive effects of these pollutants in the system. So I already explained how these materials were developed, and the kinetic parameters which was used for the multi-component adsorption modeling was already published in a study, Enyo and Wang 2022 in Environmental Technology, and Enyo and Wang 2023 in Journal of Water Process Engineering. So the data which was used for the multi-component models is already presented in these papers. So for this study, we use the extended Lagrangian, we use the Freundlich isotherm models, and we develop a new artificial neural network models. The artificial neural network models involves 12 inputs and 2 outputs. The output is the equilibrium isotype. So the inputs include the equilibrium concentration for the phenol and the CIP, the initial concentration, the pH of the solution, the contact sign in hours, the pseudo and second order kinetic rate constants, the pseudo first order rate constants, and the intraparticle diffusion constants. While the output is the equilibrium adsorption capacity for both the PAG, like the phenol, and the CIP. Also, we evaluated the interaction modeling. In a solution containing multiple pollutants, different types of interaction happen between the adsorbate molecule, which is the phenol or the CIP. So the assessment of this interaction can be effectively conducted through the utilization of metrics such as the P factor and the selectivity ratio. So these models try to show us in this multi-component system which of the pollutants with the microplastic prefer to absorb faster than the other. So the P factor, which was developed by Markey and Abdul in 1987, classified the mechanism by which other components in binary system prevents the component from adhering. So we have 2 pollutants in a system, and within that system, these 2 pollutants they compete, they fight for available sites. And the second model, which is the selectivity ratio, this one is served as a quantitative measure reflecting the affinity of an adsorbent for a specific component in the binary system. In the binary system, we have 2 components, and these models will tell us which of these pollutants is attracted more or is selected more compared to the other. So all models that were developed was evaluated using these metrics: the R square, which is the coefficient of determination, the mean square error, the root mean square error, the average absolute error, and the average absolute error, which are described in these equations. So the results. The characterization of the PET microplastic, I've discussed this previously. So this is just some result. This is the ORP, which is the oxidation reduction potential. This is the SBET, the surface area, the FCR, and the cell morphology. So this is the multi-components modeling. So the external Lagrangian isotherm for the multi-component modeling assumes uniform and equally available active sites on the adsorbents. So the Lagrangian assumes that the interaction, there is a non-interaction between the CIP and the PHE in the binary system. So both of them are freely adhered to the surface of the PET microplastic. The external Lagrangian model proves this is the external Lagrangian for the PHE in the presence of the CIP. This is the external Lagrangian for the CIP in the presence of PHE. And this is okay. So the summary of the parameter is shown here. So the Qmax, which is the molecular absorption capacity, the R square first. The R square value showed higher fitting for both the Ph.D. and the CIP for the pristine microplastic modified, but the age was fairly weak. The weakness of the age was because the model could not explain the interaction at higher concentration. And also the R square value for the extended fringe also follows similar pattern. So to develop, so this is the EF isotam for the PET driven Ph.D. and CIP binary system. So this is the final model for the extended aluminum and for the extended fringe rather. So these models can help in the prediction of the equilibrium capacity multi-component system. So the Y values are already developed. So we just need to know the concentration and we can compute this model. So to address the limitations of the extended Langmuir and extended fringe, this is the computational modeling constant, artificial neural network for the pristine. So for the pristine and HPET microplastic, we have one hidden layers, while for the mode we have 2 hidden layers in the model development. And these models, for the hidden layer, this is the calculation for the hidden layer. This is the estimate for the different hidden layers presented in the equation. These are the models for the hidden layer. And from the solution of this model, so after fine-tuning the AAN, the refined models were established to capture the absorption capacity. So these are the final models. These are the final models used for the prediction of the absorption capacity in multi-component system. So we tested these models and we found out that they have prediction capacity of 99%, while the mode showed about 97%. For the interactive mechanism, when the PF, that is the P factor, is greater than equals to 1, that means there is no impedance between the two pollutants in the system. When it is greater than 1, it means that there is impedance. So going by these results, or for example, for the selectivity ratio, in this case also, we have that the selectivity ratio was higher for the CIP compared to the phenol, which suggests that the model, the PET microplastic, preferred absorbing CIP compared to phenol. So the possible mechanism is that at the experimental pH, which was about 5.7, the phenol exists as neutral molecule because the pH is lower than the pKa value for phenol, and we experience reduced interaction between the phenol and the PET microplastic. But for the cations, for the CIP, the CIP exists as cation, and from the point zero charge, that is the ORP of the PET microplastic, the surface of the microplastic is negative. So we have higher electrostatic attraction for the CIP. So that is why the material had higher selectivity for CIP compared to phenol. So this is the graphical representation of the whole situation. In individual absorption, the molecular absorption capacity was reduced. So, but when they are both present in the solution, the molecular absorption capacity of both the phenol and CIP, of the material for phenol and CIP, increased. So, based on the P factor, the interaction is synergistic. So, however, the selectivity for the CIP of phenol by the PET microplastic was higher for the CIP. So in conclusion, the models demonstrated compatible performance metrics with capacity of up to 98 to 99%. So the finding have implication for environmental remediation and underscore the need for further exploration into the absorption behavior of different